All right, so our goal at the end of the day today is to do everything that we possibly can to try to keep YouTube from shutting down my YouTube channel again. During this day of class, there's actually a video that I'm going to show you that you're going to find really interesting. The problem with this video is the guy that recorded it recorded the chicken dance song in the background of the video. You know, the right. So I showed this video to my classes last year. Last year was the year that I transitioned to hosting my screencasts on YouTube. Showed this video to my class as a part of what we were doing in class. It's like 4 minutes long. Through the screencast online, and an hour later found out that I had violated copyright law because I don't own the rights to the chicken dance song. And I have no idea how, but they found me, and it was actually the second strike against my account because last year, remember that that show that we watched about the Manhattan Project? This I probably should have figured out. I actually posted the screencast of that so my kids could see it. What I really posted was the video in its entirety. My bad, right? I didn't even think of it. And I got dinged for it. But then the chicken dance was my second strike and they shut down my YouTube channel. So I had the option of fighting it, but if I chose to fight it and lost by simply clicking on a box that said, I don't agree and I don't think this is right, then their lawyers look at it, and if I lose, they not only shut down my YouTube channel, they completely they shut, my Gmail account gets shut down, my Google Plus account gets shut down, everything goes away. So I took the low road and just opened up another Gmail account, and now I post my videos there. So anyway, let's see if we can avoid this, shall we? So guys, today what we're going to do is we're going to talk about gas pressures and densities. Now, the trick is this. I forget, it might have been Jared. Somebody when we were grading homework said, it might have been Gavin, said something about, I just have a conceptual question. Yeah, okay. Guys, here's the scoop. It kind of piqued my interest when I heard Gavin say that, because guys, what you're going to find out is it's the conceptual stuff when we talk about gases that is the most difficult. So some of you are going to get frustrated with me. Some of you, like me, are the people that when teachers tell you, just close your eyes and imagine this, you're like, I'm not closing my eyes. This is stupid. You don't have to close your eyes. But guys, what I am going to do throughout the remainder of this unit is give you time to try to develop accurate mental models. Because guys, this is going to help you immensely as you try to understand what these gases are doing. And so you asked about the question about pressure and volume, right? Guys, those are the things that increasingly you're going to have to be able to do in your head mentally. So if you remember Gavin's question, he said, when the temperature goes down, if the plunger drops, doesn't the pressure remain the same? Dang it, that's a tough question. But guys, what you're going to have to be able to do is map your understanding to the answer to that question down to a molecular model of what gases are actually doing. So guys, what I want to do today is I want to start by filling your brain, if you will, with some of the things that you need to understand to be true about gases. And then guys, along the way, we're going to allow this to better inform our model. So I would encourage you to write these things down. So when you picture gases, I like to picture circles, spheres, maybe balloons. And then inside those balloons, guys, I place particles. And instead of them being fixed in place, I like to imagine them moving around. And the one thing that we already know is these particles are very small and the spaces around them are very big. That is Avogadro's hypothesis. Now, in addition to that, we need to understand that most of the time, the atoms that make up gases are not metallic. There are very, very few metallic gases. And I don't mean elemental. I mean contain metals whatsoever. And guys, molecules or things that tend to be gases have very low formula masses and very simple formulas. Now guys, as you guessed, there's more stuff coming, but what I'd like to do is I'd like to talk with you about why all of these things are true. You already know enough to know. So guys, let's talk about why these things are true so that you can have a more robust mental model. So let's do the first one first. Why is it, guys, that substances that tend to be gases don't contain metals? Okay, but not straight there. We have some heavy non-metals too. Go ahead.
Metals, their nature is to be either ionic or it's also sort of the way that metals bond.
Yeah.
Like, so they're very stuck together as a whole. I like to say they're communal.
I like both of those. So guys, let's talk about metals bonded to themselves. When we picture metals bonded to themselves, what do we think about? The sea of electrons, right? The communal part. But what if we have metals bonded to nonmetals? What do those form? Salts, which are so tightly stuck together that there's no way they can be gases. You guys settled with that? Okay, so now what about these, guys? Why is it that the things that tend to be gases would be low mass, simple formula substances? What do you suppose happens to molecules as they get bigger and more massive? Higher intermolecular forces. Guys, because what leads to intermolecular forces? Do you remember? Polarity, and polarity is caused by what? Dissymmetry, right? You can have polar bonds and still have a nonpolar molecule if the thing is symmetrical. So guys, you may want to be writing these thoughts down in your notes because these are critical. So why is it that metals don't form gases? Because they tend to form ionic bonds. So what about the link between mass and simplicity? And the idea is this, and maybe let me see if I can write it down. So the idea is this. So if we have higher molecular masses or higher complexity, and again, guys, my pen is dying, this leads to, let's say, it's more likely, what is non-symmetrical? Dissymmetrical? Asymmetrical. So it's more likely asymmetrical, and if it is asymmetrical, it is more likely polar, and if it is more likely polar, it will have stronger intermolecular forces, and therefore it's less likely a gas. Yeah, kind of, yes. Lex it E. How about that? But guys, you get the idea? And so if you're picturing in your brain your gas, as those particles get bigger and more massive, there's a higher likelihood that they're lopsided. They're shifted around. And if they're shifted around, that makes them polar. And if they're polar, they exhibit intermolecular forces. And if they exhibit intermolecular forces, they stick together and they are more likely liquids and solids.
Are you talking about just asymmetrical shape, or do they have to have like asymmetrical electronegative, like they have diamonds?
Exactly, and that's the idea. Assuming that they can't be all the same atom, right? So assuming they're different atoms, they have to have different electronegativities. If they have different electronegativities and they're lopsided, that makes them polar.
Yeah, but I'm just thinking like, because there could be like a bunch of weird hydrocarbons that could be like one big benzene and then just things like that are technically lopsided.
And they would more likely be a liquid and less likely a gas. No, they have to be. They would be, if they're lopsided, they are polar. That's a guarantee. If something's lopsided, if it's not symmetrical, it will be slightly polar. Yep. Okay, so guys, there's number one. Here comes number two, the physical characteristics of gases. Some of these you're comfortable with, some of them we may need to talk about. So guys, physically, gases expand to fill their containers, Tazvak. They have, therefore, the volume of the sample is equal to the volume of the container. They are highly compressible. We'll talk about that in a minute. And they form solutions with each other in all ratios, if you will. So you can't saturate a gas-gas solution. So maybe we should add that. In all proportions. There we go. Like that. And guys, again, we can talk about these as we go. Yeah. Oh no. Where did I do that wrong?
Is that right?
I don't know. I think so. You can use 2 if you'd like. 3 in total. It didn't come up on spell checker, so I'm going to go with it. You guys caught up? So let's talk about them. Number one, you're good with, right? Because the molecules are not sticking to each other, they spontaneously fill. We talked about entropy. They expand to fill the container. And therefore, guys, the volume of the sample is equal to the volume of the container. You good on that? Okay, so what about highly compressible? What does it mean and why is it true? What does it mean that something's compressible? You squeeze it and it gets smaller, right? So guys, why is it that gases would be highly compressible? All the empty space. Yeah, all you're doing is pushing those particles closer and closer together, and because they have so much empty space, it's easy for them to get smaller. Guys, that is not true of liquids and solids. That's how hydraulics work. Like if you've ever seen a front end loader and all the pipes and tubes that run around that thing, there's just a compressor that squishes the gas or the liquid inside there, the oil. But because the oil can't compress, it pushes and it causes the bucket to go up and things like that. Because you couldn't get that to work if those hoses and pipes were full of gas, because you'd try to compress the gas and all it would do is get smaller and it wouldn't push because it's so compressible. And then guys, this last one we should talk about. It says gases form solutions with each other in all proportions. So let's talk about a kind of a real world example, and that would be air. Are you guys familiar with the idea that air is a solution? Did you know that? It's mixed together. What is the predominant substance in the air we breathe? Nitrogen. It's about 80% nitrogen. You've got oxygen, carbon dioxide, helium, all the other trace gases that are in there. But guys, most of the air that we breathe is nitrogen. Now here's the trick. These are not bonded together. They are actually mixed together as a solution. Understand that it's not like salt dissolving in water because they're nonpolar. So it's not like the nitrogen is surrounding the oxygen, but we think of it as being a solution because they're mixed together, but they're not bonded together. And it is homogeneous, so it must be a solution. But guys, the trick is you can never add enough of one gas where you can't get more to dissolve. So these form in all proportions and they can never be saturated. So that's the scoop there. Yeah. Yeah. Right. So there's a couple things going on there. One is just simply density. That you know, these things settle, and because they have different masses, we have different ratios. So the heavier gases settle to the bottom, but remember that we also have wind currents and things like that that keep them mixed. And so if that weren't the case, you would get even more settling, but there's that constant mixing that goes on. But you do get concentration gradients based upon density. The more dense gases at the bottom and less dense. It also has to do with where they're formed. The chemical processes that that make ozone actually happen in our upper atmosphere, and so that's where it predominantly sits, although it really is everywhere. But the majority of it is up there, again, partially because that's where it's made, and also because that's where the wind currents take it. So, yeah, there's a lot more going on than just that. Yeah.
So is it like all air everywhere, like wherever you breathe in, it'll be the same proportion of nitrogen to oxygen?
We're going to go with yes, but what we're going to have to talk about first is something called a mole fraction, and we're going to do that next time. So if you know the total moles of gas, and that's the denominator of your fraction, and if you know the number of moles of, say, oxygen, you can set up a ratio called a mole fraction. It's moles of any particular gas divided by moles of the entire sample, and that ratio stays the same regardless of elevation. Yeah, so, yep. And we're going to actually solve some problems on that next time. You guys good on that one? All right, last thing to add to our model, and it's this, that intermolecularly, gases have very weak intermolecular forces. Their molecules are very far apart. So much so, and guys, please do not quote this number, but it's about 1,000th, about 1/10% of the volume of a gas is attributed to the matter itself. So 99.9% of the volume that a gas takes up is actually empty space. And as a result, guys, and this is going to become really important on Wednesday, these molecules behave as if the other molecules aren't even there. Again, guys, that third bullet point there is only there to sort of help you refine your model. Understand that that is not meant to be a number that you can quote. But it is about, gases are about, here at sea, well, here on the surface of the earth, whether it's sea level or not, it's about 99.9% empty space. Mm-hmm. What are we talking about? Well, yeah, so they're not ionic. I'm not a, hold on, Spencer. They're not ionic, so they're molecular. We're sort of agreeing on the idea that the things that form gases are molecular. I can't think of examples of times where they'd be like a polyatomic ion or something like that. So yeah, we're agreeing they're neutral. Polar, but neutral. Oh, absolutely, they have to. We're going to talk about that. We're going to talk about, when we get into the kinetics of gases, we'll talk about their elasticity. We're going to assume that no energy is lost in their collisions, but we'll get there in a couple days. Yeah, go ahead.
So when you breathe in,
Well, I mean, depending on what happens with, yeah, so the air that we're breathing in is 99.9% not anything. And then it concentrates in our lungs, right? And so that's not the case in our lungs. But yeah, the air we're breathing in is mostly empty space. Yeah. Yeah.
I was thinking the same person just said, how do you breathe in?
It's muscular. Yeah. So it still exerts a pressure, and as we expand our rib cage, it's literally driven down our throats by the pressure of it. And we're going to talk about that next. Yeah. Oh yeah, only for gases. Yep. You guys good? Yeah. Okay, guys, so with all of this as a background then, I wonder if maybe you could sign off on this. When I think about gases, this is where my brain goes. When I picture a gas, I picture small particles. I made them big enough that you could see them, but remember, how small should these particles be? They should only take up 0.1% of the volume of that, well, volume, area, but volume, because it's really 3D, of that entire circle. So guys, what else do we know about these particles? Well, we know that they typically are not containing metal atoms. We know that they have relatively low masses and simple structures because that keeps them from being polar. We also know that they are in motion. We know that they are colliding with the walls of the container and with one another. And that this then is maybe our fundamental model for a gas if we could set these in motion. You guys comfortable with the idea? Yeah. We will. It's called temperature, sort of. We'll get there soon. Yeah, absolutely. But temperature is an indirect measure of their velocity. And that's what, actually, temperature is a measure of kinetic energy from which we can figure out velocity and average velocities, which are more important to us. You guys okay with the model? Is there anything different or unique about the models that you're beginning to form in your mind as compared to my model? Things you would change, things you would get rid of, things you would add or include? You okay? Mm-hmm.
I like to emphasize that the reason that balloons sort of they stay in their shape.
Yes.
They're hitting a lot of places at the same time.
Good, absolutely. And we're going to talk about that next, that these particles are in fact hitting the walls, and we call the result of that collision pressure. Sometimes, absolutely. We okay? Okay, so guys, what we're going to do then is we're going to actually go where Spencer's brain is taking him, and we're now going to talk about pressure. So guys, understand that if that's your mental model needs to include the fact that these particles are moving. And as these particles move, they run into each other, but they also run into the outside of the container. Oh gosh. And guys, when they do this, just a second, I don't know what that did. Guys, when they do, oh wow, here we go. When they run into the outside of a container, they create what we call pressure. Now, here's the mistake that you're going to make. You are going to confuse pressure with force, and they are not the same thing. So guys, pressure is force over a given area. And we're going to talk about pressure in a couple contexts. But if you want to look at it mathematically, this is probably the clearest way for you to understand it, is that pressure is a force given over an area. Now guys, you're probably familiar with the units that we use for pressure here in the US, which is typically PSI, pounds per square inch, where pounds is our force. We understand that pounds is a unit of force, and then our area is square inches. But guys, there's lots of others. There's newtons per square meter. There's all, or actually, yeah, you name it. There's lots of other units. But guys, when we talk about pressure, what we need to talk about first is we need to talk about air pressure. And so you saw this last year, but let's go back to make sure that you understand this. Guys, one of the pressures that we deal with is the pressure of our atmosphere. And I think you may remember last year, I kind of said, if you look up, there's actually a column of air resting on your head that's about 10 kilometers thick. And guys, this column of air that is sitting on us literally is pushing down on us and applying a force that is actually kind of amazing. There's about 10,000 kilograms of air sitting on every square meter of area. So guys, if we've got, it's pretty close to this. So in this space, this area right here, there's about 10,000 kilograms of air sitting on there creating pressure. Now guys, the question then becomes, why are we not being smushed if we have all of these literally tons of air pushing down on top of us? What's the pressure inside of our bodies? It pushes back out. Guys, if you don't understand this, in addition to being kind of sad, it's critical that you get this. So let me see, I don't have here, let's see if we can get this to go. So guys, the idea is this, that air pressure is pushing all around us. So here's the idea. I'll bet we can make this work. This is a little impromptu, but it sounds like you guys don't understand this, so let's talk about it. So guys, the idea is this. If we've got an empty Erlenmeyer flask, there's air above it, there's air outside of it, there's air inside of it, and guys, literally, there's enough pressure pushing on this glass that it would shatter if the air were also not going in and pushing back out. But the question then becomes this: what happens when we fill this with water? Well, when we fill it with water, there's no longer air inside of it, so there's no longer air pressure pushing back out. Now, what we can do is we can then cover this up and go like this, and it doesn't come out. Now, guys, the question is why? Why is this water not just flowing out of the Erlenmeyer flask? What is supporting it? Air pressure, because right now, guys, the pressure of the atmosphere is going down, looping back up and pushing in this direction. But how much air pressure is pushing down through the Erlenmeyer flask? None, because there's no air inside there. I mean, obviously, if we do this, this is not going to stick because there's air pressure inside and outside. But when we replace the air with water, there's no longer air inside the Erlenmeyer flask. And so consequently, because there's no air pressure pushing down and only, it got soggy and bent, and only air pressure pushing up, it's actually enough pressure to support the water. Yeah. Absolutely, yeah. The water in this case, and the reason is because there's so much less of it, right? You've got 1,000 or whatever kilometers of air pushing up, and only this little itty bit of water pushing back down. And so all of that air exerts greater pressure than the water that's just inside the Erlenmeyer. Yeah. 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 Right. Mm-hmm. Well, but it's now supported by the water. So what we would have to do, because you're right that there isn't the same pressure, but there's still some pressure. So in order to really demonstrate the amount of pressure that the air is pushing on here, rather than replacing the air with water, we would just have to remove everything. And if you could draw everything out of here, a vacuum, right, then the glass would shatter. It would collapse on itself. Yeah. Go ahead. Yeah. They make the glass very, very perfect. Yeah, and understand it's not a perfect vacuum, but what happens is if you've got symmetry, you'll notice the glass bulbs tend to be rather symmetrical. The reason is because those structures support the pressure better. And I don't believe that they do draw a complete vacuum on them, but you're right. And if you ever ting a light bulb just right, and it implodes. Yeah, it's on the verge for sure. So guys, just a second. You okay with the idea of pressure? You get the idea? But guys, it's critical again that you understand that this is a force over an area. So the force comes from the air, and then the area is actually the area that it's being exerted upon. So guys, as a result, then we've got this idea that this force is actually the result of the downward force of gravity acting on the air. Now guys, our units for this are typically pascals, where a pascal is 1 Newton of force over 1 square meter. Now guys, the problem is that is a ridiculously small amount of force, and so we commonly use kilopascals because that is an amount that makes more sense given the types of pressures that we see. But guys, again, the trick here is that you've got to be thinking pressure and not just force. And I'll give you an example of something that maybe will help you make sense of that in just a second. But again, guys, the critical concept is pressure and not just force.
So a good way to think about it is that the glass will shatter is that it's not that the air is coming in but it's also coming out, flying out because it's moving so fast.
but that's not true. Yeah, it's sealed. Yeah, it's just supporting the pressure. Yeah, go ahead, Everett.
Is Pascal like that?
Yeah, after blaze. Yeah, it's blaze. Yeah, yep. Yeah, absolutely. Yeah, Blaise Pascal. Okay. Yeah, his first name was Blaze. Yeah, isn't that cool? Yeah. Okay, so guys, let's make sense of this then. You ready? It's pressure and not force. To help you sort that out in your brain, and maybe some of you have heard this before, but when I first heard it, it was surprising to me. So imagine an elephant. Okay, if you've been to the Hogle Zoo, you've seen elephants. So you've got an elephant, those things weigh tons, right? But what is weight a measure of? They literally weigh tons, but weight is force, right? Weight is a force. Now imagine a fashion model in stiletto heels. Weighs a lot less, right? But you ready for this? 100-pound, well, 120-pound maybe, 120-pound fashion model in stiletto heels, you know, those really crazy spiky heels? Guys, a fashion model in stiletto heels actually exerts a greater pressure on the ground than an elephant. Make sense of that though, guys. How can that be? What's the thing that doesn't initially come to mind that makes that sound ridiculous until you think about it? The area, right? An elephant's foot is so huge that those tons of weight are distributed across such a large area that the pressure is very low. Whereas, you know, a 120-pound woman in stiletto heels weighs a lot less, but I mean, the point of a stiletto heel is like the size of your pointer finger, right? And you've got that weight concentrated in such a small area that the pressure is actually greater. Do you see? Exactly the same idea. That's why fat bike. That's why when you go to Moab, you decrease the pressure in your tires, because when you decrease the pressure in your tires, they flatten. You get a bigger they call it contact patch, and consequently, you spread out your weight over a greater area. Therefore, there's less pressure. You get the idea? Okay, so guys, the question then becomes, how do we measure this pressure? And for those of you that are in lab, we just talked about this today. For those of you that aren't in lab, we talked about it last year. Guys, we measure pressure using what we call a barometer. Now guys, all a barometer is a column of mercury that is supported by atmospheric pressure. So when we talk about a barometer, we look at something that looks like this. And so it should maybe sound familiar to you from last year or even earlier this morning, that the idea is that we've got air pressure pushing down on a vat of mercury. That vat of mercury has the option of going up a glass tube where there's a vacuum drawn at the top. Because there's a vacuum, there's no pressure pushing down here. And then we talk about atmospheric pressure being measured in units of length, because we measure atmospheric pressure by talking about how high is the column of mercury that the atmosphere supports. So guys, if you're watching the Channel 4 news tonight, and if the weather person gets on and says the atmospheric pressure or the barometer is reading 27.8 and falling, what are the units? 27.8 what? Not centimeters, not kilopascals, not torr. Think about 27 torr. Standard pressure is 760. That would be bad. What are the units? Guys, inches of mercury. Here in the US, we use the units inches of mercury. So when you watch the news and they say 27.8, that's inches of mercury. We, on the other hand, use millimeters of mercury, which are equivalent to torr. Now guys, the question is this: why do we use mercury in the first place? Maybe, but no. Why do we use mercury? What's unique about mercury? What's that? It's very dense. Guys, there is no reason that you can't build a barometer out of water. It would work just fine. The problem is it would have to be, I did the math once, it would have to be like 30 feet tall. Really. The idea is that if you were using a water barometer, because water is so much less dense, you would have a much higher column of water than you would mercury, and it just wouldn't be practical. Because if you understand the ramifications of that, maybe it's interesting to think about it this way. What that means is there's a theoretical limit to how long a straw can be. Right? Because when you drink water, or whatever, say water, when you drink water through a straw, guys, you are not sucking the water into the straw. You are removing the air from the top of the straw, and then atmospheric pressure drives the water into your mouth. And so you can only drink through a straw. You can only drink through a straw that is less than the length of the column of water that our atmosphere will support. It's like 27 feet. But if you think about it this way, it may make more sense. If you're trying to drink mercury, really, guys, if you're trying to drink mercury, hold on. Listen, if you're trying to drink mercury, that straw cannot be longer than the atmospheric pressure measured in millimeters of mercury, because you can't suck the mercury up any higher than a vacuum will cause it to rise. Yeah. Mm-hmm. Yeah. Yeah. That's the idea, that what you're doing is you're removing air, and air is rushing in to meet it, because now if you've just got a little bit of drink, it's no longer the water being driven or whatever you're drinking up the straw. There's also room for air to replace it as well, so you're getting air and liquid as well. Yeah, yeah.
So this is, I think, the section of the song where it was like, is it easier to really drink from straw on bars?
Right. Because that's what you do. Yeah, yeah. Well, so the difficult part about the question, I don't think that's quite how it's written, is what do you mean by easier? Because if you really mean easier in terms of less work, that's a whole different conversation. But in a vacuum, say that, let's go to the extreme, because Mars has some atmosphere, but say you're out in the space shuttle. Okay, but you understand that they pressurize the space shuttle, right? So they don't have their helmets on, they can breathe. But imagine if you could be in outer space and not explode. But if you were in outer space, you can't drink through a straw. It doesn't work. Yeah, because there's no air pressure. If there's no air pressure, straws don't work. So if you then go somewhere in between, right? Because in outer space, straws don't work. Here on the Earth, they work great. So what about on Mars? Well, on Mars, there's less. It is less, right? I think it's less. There's less air pressure. So therefore, you'd have to remove more atmosphere above in order to drive in the remaining liquid, because there's less push. So it would be, maybe we could say straws would be less effective, or they would be effective over a shorter length. So maybe on Mars, you could have a straw that would be longer than could functionally work. You know what I'm saying? Yeah. How did that fit in with the conversation you had with your dad? You just remember tension. Okay. Yeah, 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 yeah. It's sort of a reconceptualization though, right? To think about it's actually the atmosphere pushing the liquid up. Yeah. So guys, when we then talk about these ideas of pressure, none of these are a surprise to you, but these are the units maybe we should make sure that we're comfortable with. We understand that we measure pressures. All of these are equal to 1 atmosphere at 760 torr or millimeters of mercury, 101.3 kPa, and these all equal 1 atmosphere. You guys good? How about this? You okay? Okay, so now guys, the question becomes this. How do we take this idea? Which idea? How do we take this idea of a barometer and use it to measure the pressure of gases that aren't our atmosphere? Do you see where we're going? So barometers work great when the gas that you're trying to measure the pressure of is the atmosphere. But how do we measure the pressure of gases that aren't our atmosphere? And guys, you have some experience with this because you've all checked the pressure in your tires and use a pressure gauge. But in a chemistry lab, we actually use something a little different called a manometer. So guys, this you want to scratch down in your notes. It's also located on page, let me make sure this is the right page. You may even want to look in your books. Yeah, if you look on page 387. So guys, when we measure the pressure of gases, we use a thing called a manometer. And specifically, you need to know how an open-end manometer works. So this is basically a barometer that allows you to measure the pressure of a gas relative to atmospheric pressure. Again, it's on page 387 if you want to look, but it looks like this. And you'll see that there are pictures of this sprinkled around page 387 and elsewhere, but it is on 387, also a little bit on 388. Because you've got to understand how to work these conceptually and mathematically with manometers. What I'm going to do, did you get all of this down? Are you okay? Just the note part, the manometer part. Let me try to draw these with you. And guys, you know how poorly my board is behaving, but let me see if we can just do this together. So this is the idea. Draw yourself, come on baby, give me a circle. And then like this, you gonna do that for me? No? Like that. Come on. And really? Oh my good heavens. I'm gonna just do this on the board. Maybe. All right. So guys, the idea is this. You've got a sample of gas and you've got a tube that goes like this. And this is functionally what a manometer looks like. It's a U-tube. So it's a U-shaped tube that is hooked up to a sample of gas. So this is your gas sample right here. And then inside this U-shaped tube, you've actually got a liquid. It could be mercury, it could be water. It actually doesn't matter. But you've got a liquid in here. Now guys, are you all familiar with the idea that liquids try to seek their own level? Are you familiar with that concept? Let's talk about it. So the idea is this. If you've got just a U-shaped tube, and that could be a tube of glass, it could be a tube of rubber, it doesn't matter, but if you pour water into this, the water levels will be the same on both sides. You familiar with that idea? See if this pen works better. So guys, come on baby. It's not better. But so guys, why is that true? Why would they seek their own level? Why would those water levels be the same? Pressure is the same, right? Because the air is pushing down here, the air is pushing down here, and therefore the pressures are the same, therefore the levels are the same. Now guys, imagine this. Imagine that you take this end of the tube and hook it up to a sample. So now, what is pushing down on that side of the tube? The atmosphere. What is pushing down on this side of the tube? The gas sample. So this is the idea. This is the pressure of the atmosphere. This is the pressure of the gas sample. Now let's say, for example, that we make our liquid then mercury. So what's going to happen? Well, let's talk about some potential outcomes. What do we know if these two levels are the same? Pressure of the gas is the pressure of the atmosphere. Now guys, what if we get this? What if this side is low and this side is high? Which pressure is greater, the sample or the atmosphere? The sample, right? So what we can do then is we can measure this height in millimeters. So say that we know the pressure of the atmosphere is 760 millimeters of mercury, and say that this height is 20 millimeters of mercury. What is the pressure of that gas? 780 millimeters of mercury, or 780 torr. So the idea is if this side is lower, you add the height of that mercury column to the pressure of the atmosphere. Now guys, what if it goes the other way? What if we get this? What if this is up here and this is down here? Now which pressure is greater? The pressure of the atmosphere, and then we would subtract that pressure from the pressure of the atmosphere. You get the idea? Yeah, Vanessa. No, it's the height from the, good question. It's the height from this level to this level. So it's literally the difference in their heights. Well, and that's the idea. Say that this is our data. Okay, so we measure the difference in their heights and it's 20 millimeters of mercury. Okay, I'm just making up numbers. But say that we measure the atmospheric pressure at 760 with a barometer. So if the atmospheric pressure is 760 and this height difference is 20, which pressure is greater? The pressure of the atmosphere or the pressure of the gas sample? The atmosphere is greater, so the pressure of the gas sample would then be 760, the pressure of the atmosphere, minus 20. So it would be 740. Does that make sense? You guys okay with how manometers function? Yeah. That's the thing that's interesting. Well, you don't to find its pressure. Yeah, but potentially it depends on what it's hooked up to. We're just talking pressure now, though. So, you guys good on manometers? Go ahead. Yeah. It does, so long as it's not kinked. Absolutely. Yeah. Let me do this quickly, and then we're going to talk. Then we're going to talk density really quick. But here's my house. Okay. Here is a board that I screwed to my house to build a deck. Real world stuff here. Okay. So I built the deck on the back of my house, and the first thing you do is you screw a ledger board to the side of your house. Then my deck is 30 feet off the house. Okay, so what I need to do is I then put a post in the ground over here, and I needed to screw a board to this post that I could then put the joists in to build my deck on. But I needed this to be exactly the same height as that. So how do you do it? Well, what you do is you buy a hose that's as long as the distance you want to go, and you fill the hose with water. It's got to be clear so you can see the water. But then what you do is you send your wife over to the house and you say, hey, Carla, hold this up against the top of this board and make sure the water level is right at the top of the board. And then I grab the other side of the hose, even though it's all across the ground and up. And as soon as this water level, well, this water level will always be the same as this water level. And so long as this water level's here, then I know how high to put this board so that they're perfectly level to make my deck flat. You get the idea? So it doesn't matter how much wiggle it does there. Yeah, I mean, it's a great way to measure it because all of this doesn't matter so long as it forms a U. Okay, but your hypothetical is just saying you built a really bad manometer. Okay. So guys, we are now going to move on and we're going to talk about gas densities. We're going to reconnect this to your concepts. And guys, all of this comes with a warning. I'm glad that you're appreciating some of the interesting things that we can do as we talk about gases. I'm willing to go with you there as much as you want. Here's the problem. If we continue to run down rat trails, you just take your test after Christmas. Your call. So let's talk about gas densities. So guys, as we talk about gas densities, what you're going to find is if you take Pivnert and if you finagle it a little bit, and the book actually talks with you about the finagling. If you take gas densities and finagle it a bit, you can actually arrive at this equation, which you want to write down. This is not on the AP equation sheet. But they expect you to know it. The reason that they expect you to know it is because these are things that you can come up with based upon your mental model of gases. So what do we have here? Well, guys, D is density. This is the density of a gas. So what is the density of a gas related to? Well, guys, we understand that density is a measure of, shall we say, compactness, maybe. We talked about the idea when we learned density a year ago that if we have a sample of aluminum, both of these samples have the same mass. There's the same amount of aluminum in this block as there is in this aluminum wool. The difference is that the block is more compacted and therefore more dense. So guys, we can have similar thoughts and conversations around the density of gases. The density of gases is proportional to the molecular mass. M is molecular mass and P is pressure. It's inversely related to R. But guys, R is a constant, so we don't need to worry about it. It is also inversely related to temperature. So guys, we're going to stress test your mental models. We're going to do it mathematically, then we're going to do it conceptually and make sure that the points line up in your head. So guys, again, D is density. M is molecular mass, P is pressure, R is the universal gas constant, and then T is temperature. So let's talk about it first mathematically. As the molecular mass of a gas goes up, what happens to its density? Goes up. As the pressure goes up, what happens to the density of the gas? It goes up. As the temperature goes up, what happens to the density of the gas? It goes down. Now understand, guys, that this is always assuming that nothing else changes. Getting us, Gavin, back to your thought about what if temperature and volume both change and things like that. We're assuming that the others are not changing. So as the molecular mass goes up, density goes up. As the pressure goes up, the density goes up. And as the temperature goes up, the density goes down. You good? Okay. Now, guys, take these ideas and let's use my mental model as a place to maybe understand, why these things are true. So if we go back and if we take my mental model, why will it not let me grab that? Come on, right here. I am so sick of this. Okay, we're just gonna have to do it like this. And, we're going to have to do it like this. Oh, okay, here we go. We're going to have to do it like this, guys, but this is the best we can do. So here's my mental model of a gas. So what is representative of density in this picture? What are you seeing that would represent density? How many molecules per volume, per area, maybe how tightly packed together they are? So guys, let's do this. What would change in this model if we talk about the molecular mass, one of the variables? If we talk about the molecular mass going up, what would change in your, maybe our, mental model that would represent the molecular mass changing? How would your model be different if you then got a different gas with a higher molecular mass? Would the dots get bigger? Not much, right? That's Avogadro's principle. It doesn't matter what the gas is. The molecules are all about the same size. Not more dots, because that would be more moles. And not necessarily closer together because we're not changing anything else. So how would your model change? Guys, it's a tricky question. The answer is visually it wouldn't. The molecules wouldn't be a lot bigger because more massive molecules are not a lot bigger than less massive molecules on the scale of the free space around them. So what you're going to have to do is you're going to have to tweak your mental model to allow you to see that what's really happening is while the molecules don't look a lot different, they are heavier. And if they are heavier and occupy the same volume, what happens to density? It goes up. Do you get the idea? Now let's talk about the ones that change. What about pressure? How would our model change if we increase the pressure? What does Boyle's law say? If we increase the pressure, what happens? It gets smaller, and what happens to density? It increases. Now guys, what about temperature? As temperature goes up, what does Charles' law say will happen? It will get bigger and the density goes down. So increased pressure, it gets smaller and more dense. Increased temperature, it gets bigger and less dense. You good? Okay, so guys, let me give you your homework. Here you go. And we will go on Wednesday.